Okay, the next talk is on dynamic cube attacks against grain 128 AEAD, and the talk is by Chen Liu and Tian Tian, but against all odds, it's given by Yinu Liu, if I'm informed correctly.
Thanks for the introduction. I'm Yinu Liu. The two authors of this paper and I are in the same research group. Because they could not attend this conference, I will give this talk instead. First, I give an introduction to cube attacks and dynamic cube attacks against stream ciphers. For stream ciphers, every output key stream bit can be written as a Boole function of security key variables and every variables. Let I be a set of indents of every variables, namely cube indents. The every variables indexed by I is called cube variables or active variables. Then F can be uniquely written in such a form where Ti is the product of cube variables and each term of Qi is not a multiple of Ti. The polynomial Pi is called the superpoly of I in F. The process of cube attacks includes offline and online phases. The offline phase is independent of keys, and the main aim of this phase is recovering the number of superpolies. In the online phase, calculate the value of the superpoly under the key and solve the system of equations built upon superpolies to recover key information. The dynamic cube attack is a variant of cube attacks, which is extensively applied to the green family of ciphers. The basic idea of dynamic cube attacks is to simplify or even nullify the ANFs of several critical intermediate state bits. This is achieved by imposing dynamic constraints on certain IV variables, which are referred to as dynamic variables. Guess the values of key variables or expressions involved in the constraints. We can identify the correct guess based on the Bell's phenomenon of certain superpolies. Next, we introduce our motivation. Recall that in the paper, links between division property and other cube attack variants presented at FSE 2020, the authors pointed out the previous dynamic cube attacks were theoretically unreliable due to the absence of theoretical discussion of randomness for the wrong key guess. Besides, the authors proposed that for a given nullification strategy, a qualified cube should satisfy the following conditions. For the correct key guess, the superpoly is zero constant, and for a wrong key guess, the superpoly has high degree with a Bell smaller than 2 minus 1. Third, the authors proposed a theoretical method for estimating the Bells of superpolies based on a heuristic assumption. However, we found that the dynamic cube attack against the 4 green 128 proposed in that paper was invalid. There are two main reasons for this. First, the MILP modeling technique for the dynamic cube attack did not consider the structural characteristics of the green family. As a result, the established MILP models contain numerous redundant division trees. Second, there is a significant gap between the theoretical Bells estimated and the actual Bells. After extensive experimental validation, we found that the assumption used in the paper is not universally applicable to the green family of ciphers. Therefore, the qualified cubes constraint in that paper failed to effectively distinguish between correct and wrong key guesses. Our main contribution is to present a more robust dynamic cube attack against the green family of ciphers. In specific, it consists of the following three aspects. First, we introduce heuristic technique called the polynomial approximation with respect to Bayes, which could provide a more accurate Bayes evaluation for superpoly of a high-dimensional cube. Second, we proposed a more accurate MILP modeling method based on the three-subset division property without unknown subset, which takes the structural characteristics of the green family into consideration. Third, we proposed a method to analyze the impact of Ronchi gases on superpolies from an algebra perspective. This method aims to identify all possible Ronchi gases that are at least distinguishable from the character key gas. As applications, we present a key recovery attack against the 190 round green 128 AEAD with theoretical analysis of the success probability, which is the first dynamic cube attack against the green 128 AEAD. Then, based on the new modeling technique, we further discuss the feasibility of previous dynamic cube attack given at the FSE 2020 against the 4 green 128. Finally, we compare the accuracy of our Bayes estimation method with that of the previous method by performing experiments on the reduced round green 128 AEAD. Next, I shall introduce our new work. The first technique I will introduce is the heuristic method called PAB. Before representing the new method, I will describe a trivial method for calculating the Bayes of Boole function. In fact, if we could recover the exact ANF of the superpoly, we can assess the practical Bayes by conducting a frequency test. The process of conducting a frequency test is straightforward. First, calculate the output values for n random input values. Subsequently, the Bayes epsilon is computed by this formula. If n is not larger than this value, then epsilon can be considered as the Bayes of the superpoly. However, as the number of rounds increases, it becomes extremely difficult to recover the entire superpoly. Therefore, we proposed the PAB technique, a heuristic method to estimate the Bayes in the superpolies of high-dimensional cubes. The core idea of the PAB technique to construct a simple polynomial with a Bayes similar to the Tigit superpoly. To achieve this, our main idea is to recover a portion of the complete superpoly and replace the remaining parts for a simple polynomial with similar Bayes. Then the Bayes of the superpoly can be calculated by detecting the Bayes of approximate polynomial. In specific, by employing the divide and conquer algorithm for polynomial recovery, we use the MILP modeling to resolve each monomial involved in the superpoly. We set a time limit for a given cube I naught by PS, the sum of all nominals of the superpoly Pi that could be recovered efficiently using MILP solvers, and not by Pu, the sum of monomers and could not be recovered by MILP solvers within the time limit. Then we decompose the polynomial Pu in the following form. Note that the polynomial cube omega is still very complex, whose ANF is unknown. Replace each polynomial q omega by a new variable x omega yards, and we get an approximate polynomial pi prime. We provide a set of polynomial transformation rules to express Pu in the desirable form, which avoids introducing too many new variables. To evaluate the Bayes of each q omega, we introduced a new algebraic property of polynomials called the minimum algebraic degree. Based on this algebraic property, we propose a heuristic method for estimating the probability distribution of Q omega. Set the following probability distribution to the new variable x omega. Then it's easy for us to compute the Bayes of Pi prime, which is treated as the approximation of the Bayes of the superpoly Pi. Then it's easy for us to compute the Bayes of Pi prime, which is treated as an approximation of the Bayes of the superpoly Pi. Next, I will introduce a new MILP modeling technique for dynamic Kubo-Torx digitated as a green family of ciphers. Compared to the original MILP modeling method proposed at FSE 2020, the new modeling technique are more accurate. First, it is known that the three subsets division property without unknown subset is more accurate than the conventional bit-based division property, and the new modeling technique is based on the three subset division property without unknown subset, while the original model is based on the conventional bit-based division property. The second improvement involves optimizing the constraints of the update function of the green family of ciphers used in the MILP models. In the original model, the monomial marked in red appears in the following equation, which leads to redundant division trails in the model. The optimized constraints ensure the monomial no longer appears in this equation within the MILP modeling, thus avoiding many redundant division trails. The third implement is that we incorporate the algebraic relationships derived from the nullification strategy as constraints in the new models. This method can be improved the accuracy of the solutions returned by the model. Based on the 3 points mentioned above, we propose the new MILP model for dynamic Kubo-Torx. This model can accurately detect the algebraic properties of the corresponding superpolies under various key guesses, including but not true algebraic degree, minimal algebraic degree, and divisional reasons. Next, I briefly introduce how to analyze the impact of wrong key guesses in the superpoly from an algebraic perspective using the nullification strategy NS as an example. Under nullification strategy, the key variables and the expressions that are needed to be guessed are G30, K42, and K125, with not their guessed values as G30 prime, K42 prime, and K125 prime. That mu0, mu1, mu2 satisfy the following relationship with the key guesses. Therefore, different values of mu0, mu1, mu2 correspond to different key guesses. Clearly, when the character key is guessed, the value of mu0, mu1, mu2 are 0. The superpoly Pi can be expressed in the following form. Moreover, depending on the value of mu, the superpoly will show different levels of complexities. Based on the above methods, we implemented the dynamic Kubo-Torx on 190 round green 128 AED. In our talk, identified the nullification strategy by employing an automated search algorithm. It only nullifies the two internal state bits by guessing 6 key bits. As a result, our attack provides 3 bits of key information with a complexity of 2 to the power of 103.44 and a theoretical estimated success properties of 99.68%. We then provide the further discussion on the feasibility of the dynamic cube attack against 4 green 128. To further investigate the structural characteristics of green 128, we adapted to recover the superpolice of the 4 version of green 128 without employing only any nullification strategies. As a result, we successfully recovered the superpolice of a set of cubes with 80 dimensions. We observe that the all recovered superpolice have nullificant bias close to 2 to -1, along with both a high algebraic degree and a high minimal algebraic degree. Additionally, these superpoli are very sparse. Based on the experimental results presented above, we infer that the superpolice of high dimension cubes in the 4 green 128 generally exhibited significant bias, along with both a high algebraic degree and a high minimal algebraic degree. Therefore, within the current framework of the dynamic cube attack, we believe that it is challenging to conduct key recovery attacks solely by modify the nullification strategy. We compare the accuracy of the bias estimation method based on the PAB technique with that of the method using the minimal splits set given at FSE 2020 through experimental testing on the reduced round green 128 AEAD. It can be seen from the table that the accuracy of the PAB technique significantly better than the previous minimal split set method for green 128 AEAD. At last, I gave a conclusion to this talk. In this talk, we introduced a robust implementation of dynamic cube attacks against the green family of ciphers. As a result, we gave a key recovery attack on 190 round the green 128 AEAD and discuss the feasibility of dynamic cube attack on the 4 version of green 128. Although it is widely believed that green 128 is unsecure, a theoretical reliable attack is still absent. Giving a reliable key recovery attack against the 4 green 128 will be one introduction of our future work. Additionally, the PAB technique proposed in this talk is a general tool for evaluating the bias of Boolean function. We think it will be useful in some other attacks. For instance, the differential linear cryptanalysis. This will be another direction of our future work. If you have any question about this talk, please feel free to contact Tian Tian. Thanks for your attention.